waiting for someone else?
Yep, please go ahead.
Yeah, sure. It's a previous presentation. That's why we see the UT logo below. So I'll be talking about local competition and stochasticity as a nexus for next generation deep learning. It's a work that we've been working for the past 3 years since my PhD. I was working in the National Capital University of Athens and the Cyprus University of Technology. And we have some interesting results about this. So we know that deep neural networks offer the state-of-the-art results in many machine learning tasks, when especially we have high dimensional data that have a hidden latent structure, that we need to learn some representations. Basically, the multi-layer rationale, the multi-layer structure of the deep neural networks provides a way of learning how to extract some efficient representations of the salient information that reside in the data. So we can use deep neural networks to, let's say, compress some information about the salient information that reside therein. However, there are many problems with deep neural networks. The first and the most well-known is that they need the hundreds of millions of parameters in order to achieve state-of-the-art performance. And this is in all the considered tasks, from machine vision to translation, the BERT models with billions and trillions of parameters. And this induces heavy memory and computational footprints. Moreover, and this is especially important, they're highly susceptible to adversarial attacks. What are the adversarial attacks? They are basically cleverly crafted examples that their sole purpose is to fool a system, a trained system, into false recognition, into misclassification, if you like. So if we have a system that has learned to recognize something, some pictures, let's say from the CIFAR dataset, a dog, and they will try, the adversarial examples will try to classify that picture with minor modifications, imperceivable by the human eye. They will try to fool the system into recognizing as something else, let's say as a cat. One extra point is that the extracted representations of the deep neural network, as we know, in most cases, there are some works that try to tackle this problem, is that they do not generalize well across tasks. This imposes heavy computational cost, extra from the memory and computational footprints that we mentioned before, and the associated annotation requirements in order for these models to generalize. So our work draws inspiration from the brain structure of mammals. It has been shown that there exist lateral connections among blocks of neurons which compete for their firing. Thus, we have a local competition scheme where we have neurons aggregated into blocks that compete to produce a specific output. This leads to a local winner-takes-all rationale, and that we will explain in the following slides. Moreover, it appears that this mechanism is of stochastic nature. So the same system that we have, the neurons, may produce different results when presented with exactly the same stimulus at multiple times. So we may give the same input every time, but get a different result. So we posit in our work that stochasticity may be a crucial part for endowing the learned representations and the representations of deep neural networks with a capacity to generalize better within a task, across tasks, and address some of the drawbacks that we mentioned before, such as adversarial attacks. What we're contributing in our work, it's a novel deep network paradigm founding upon such concepts of local competition and stochasticity. Local competition, as we explain in the following slides, yields a sparse output in each layer. So we have blocks of competing neurons, as we said before, and only one unit produces a non-zero output. The rest produce a zero value. There are some graphical illustrations in the following slides. It will be easier to grasp this notion. This unit that produces the non-zero output is determined by the outcome of the local competition among linear units within its block. So as we will see, we have linear units. So in a dense layer, we have the standard inner product computation, and the winner passed this inner product computation to the next layer without involving any non-linearity, such as Relus, Gelus, and all these variants. The main source of stochasticity that we posit, we said that in nature, in the brain of mammals, competition seems to be stochastic. So we need to incorporate stochasticity in our proposed work. And we do that by positing that competition is stochastic. So the winner is determined through a sampling procedure from appropriate categorical or, let's say, discrete posterior. This leads to the model that's the stochastic local winner takes all. Let's begin with conventional architecture, our RLU-based architecture, a deep neural network. And this is the dense layer model. So we have some observations X, and each layer comprises, let's say, K nonlinear units. We have the weight of the synapses that are denoted by W, and each unit in each layer computes the standard inner product operation with an input to the specific layer. Then we apply a nonlinear activation, and the final linear output of the layer, is given by the equation that we see on this slide. So basically, we have the inner product computation plus the bias passed through a nonlinear activation for each different unit, and we have the layer output. Now let's move. Sorry, it doesn't want to change pages. Yeah. So let's move to the LWTA-type architecture. So we said LWTA is local winner takes all, and we're now going to describe the rationale. As we can see in this slide, the singular non-linear units, the ReLU units that we saw in the previous slide, are replaced by blocks of competing units. So we see here that we have blocks of 2 units. We can have blocks of multiple units, 3, 4, 6, 12, whatever you like. And these compete for their firing. So how does it work? We have some observation X. As we saw in the previous slide, we have the synapses from the input, from the dimension of the input to each non-linear unit in the specific layer. In this case, we have the weight synapses as a 3-dimensional matrix. So that's each feature of the input, its dimension of the input, is presented to each block B. You can see here we have an LWTA block here, 1, and an LWTA block B, and LWTA blocks in between. So each dimension of the input is presented to each block and each unit therein. So what happens next is that each unit in each block computes the standard inner product computation as we described in the conventional architectures. So the inner product operation, you see this equation right here. And then instead of applying the nonlinear activation functions, let's say the ReLU, we apply a competition function in order to determine the outcome of the competition in each of these specific LWTA blocks. So basically, the rationale is pretty simple if you think about it. Each unit computes a linear activation. That's also done in the conventional case. Then instead of the non-linearity, we have grouping of linear units that compete for their firing. So instead of a non-linear function, we have a competition function. So the output of each block and each unit therein is determined by the outcome of the competition in the whole block. We will see that how it works, how we implement this in stochastic way. We can say for now that the existing LWTA approaches usually employ an argmax kind of approach for the winner selection, so that the winner unit in its block is that unit that has the greatest linear computation. So if in the previous slide, if the response, the inner product computation of the first unit is larger, numerically larger than the activation, the inner product activation of the second unit, the first unit is deemed the winner. You see the bold notation here, and gets to pass its output to the next layer, while the other unit passes a 0 value. This creates a lot of problems, both that we need some kind of relaxations or approximations in order to do efficient backpropagation training. Okay, that's a standard in many libraries nowadays, but in the beginning it was very difficult. But the most important part is that it does not respect the major aspect of biological systems that we are trying to base our models on, and that is stochasticity. So basically what are we saying in this work is that we postulate that the local competition in this block is performed via a competitive random sampling procedure. So we teach the paradigm of the argmax approach, and we say that the concept that we're implementing right now is that the higher the linear computation of a specific unit, the higher the probability of it being the winner. But it's not something deterministic as it was in the argmax approach. It's probabilistic. So the winner in each block is selected stochastically. It may have a higher probability of being the winner if it has the highest linear computation. But again, some else unit may be the winner via the stochastic mechanism that we introduce. And to do that, we introduce appropriate discrete latent vectors in order to encode the outcome of the competition in each block. Let's see that schematically. So we had the observations X. We said that the synapses are now organized in a three-dimensional matrix, such as the input J of the dimension J of its input is presented to all the blocks and units therein, and its unit in each block computes the standard inner product computation. We said that we introduce some discrete latent variables, we call them Xi, in order to denote the outcome of the competition in each block. So Xi tells us, Xi of B, Xi of 1, let's say, tells us which unit is the winner in the block 1, and Xi B will tell us which is the unit, capital B, will tell us which is the winner in the final block of the layer. These are vectors that have a one-hot representation. That means that they only have only one non-zero element that denotes the position of the winner. So basically, in the first block, we see that the first unit is the winner. So the representations Xi of 1 would be 1 and 0, denoting that the first unit is the winner and the second unit is the loser in this case. The same applies, let's say, to the second layer, the last block of the second layer, Xi of capital B for the second layer, that Xi of capital B be 0, 1, denoting that the second unit is the winner. And if we go and multiply the inner product computations that each unit performs in each block with that latent, binary latent indicator, discrete latent indicator Xi, we will get the desired output. So the winner unit will get to pass its output to the next layer, while the rest are multiplied by a 0 value. So they will pass a 0 value to the output of the layer, to the next layer, or to the final classification loss, or whatever loss are we using. In order to impose some probabilistic form in these latent indicators, we consider an approximate variational posterior of the following form. So we see that we have a categorical distribution, and we said that the intuition behind this competitive random sampling procedure is that the higher the linear activation, the linear value, the linear inner product computation of each unit, the higher should be the probability of it being the winner. So how we do that? We compute, each unit computes its linear activation in the block. Let's say you have a specific block. Its linear unit computes its activation. We pass these activations through a softmax operation. Thus, we are converting the linear activations to probabilities. And we use these probabilities as probabilities to draw samples from categorical distributions, so that we can both impose the constraint that the constraint intuition that the higher the linear value, the higher the chance of a specific unit being drawn as the winner, and at the same time allow for efficient and data-driven optimization of these latent vectors. In order to train the considered models, and since we have latent variables that are assigned probability distributions, we resort to evidence lower bound maximization for efficient training schemes. Usually these are dependent on posterior expectations with respect to latent variables, and in our case, the latent variable winner indicators Xi. And we need some way of approximating these expectations in order to perform the efficient training, because usually these are intractable. What we'll do in this work is that we approximate these expectations via Monte Carlo sampling. This is very usual in the variational base literature. So we're basically doing stochastic grading variational base, and we need a way to getting low variance gradients in order to do that. Because as you know, if we have discrete samples, let's say from the categorical distribution that we see on this slide, we can do, there is very high variance for training with such discrete vectors. So in order to solve this issue of how to get low variance gradients of our latent variables, of our expectations, we resort to the Gumbel softmax parameterization. This is the Gumbel softmax trick is used in order to produce a relaxation of the categorical distribution, so that when we draw a sample from the Gumbel softmax distribution, or the concrete distribution, if you like, it was a work from two different research groups at the same time. One called them the Gumbel softmax trick, and the other called it the concrete distribution. When we draw sample from such a concrete distribution, what actually happens is that we don't get exactly 0 or 1 values, but we get values in between, in the simplex. And these are defined in terms of a specific parameters called tau, and that controls the degree of the relaxation. So if the temperature tau is very small, it's close to 0, then the approximation is very close to the original categorical distribution. If instead tau has a large value, then we get something like a uniform distribution, depending on the size of the vector. This enables backpropagation with the discrete latent variables, let's say, in quotes. This is during training, and assures low variance gradings using only one Monte Carlo sample. So in all our experiments, usually we use, well, not usually, all the time, we usually one Monte Carlo sample in order to estimate the expectations for the evidence lower bound loss function. Turning to prediction now, we usually resort to Bayesian averaging. So what we're doing is that we draw multiple samples Xi directly from the posterior, but the categorical posterior, not the relaxation, because we don't need low variance gradients during inference, during prediction. So we draw multiple samples from the original distribution and compute the corresponding output logics, let's say, of the classifier, if we're doing classification. And then we take an average of these different results in order to produce the final classification accuracy, for example. There are some, depending on the application, there are some minor, there may be some minor differences in the final result. As you use more samples, usually in the Bayesian literature, you get a better estimation of the, let's say, classification accuracy. If you use less samples, the inference algorithm is much quicker. There is a sweet spot usually, and we're around 4 or 5 samples. Sorry. Now, a brief mention in someone might ask, what are you doing in the convolutional case? Because, okay, we were talking about the feed-forward dense layers. That was easy. Let's say we had the original nonlinear units performing inner product computations. Okay, we group them together. We transform the probabilities via softmax, and that's it. Now there are convolutional models that are very popular in many disciplines of deep learning and machine learning in general, including representation learning, computer vision, and all that. So we need to devise a variant. We needed to devise a variant in order to accommodate for such convolutional operations. What are we doing here is that in our approach, we treat each kernel, you know that each convolutional layer has some kernels, so each kernel is treated in an LWTA block. And now in this case, we're grouping essentially linear feature maps of kernels. So a kernel may have 2 or 3 feature maps, 4 or 5, let's say, and we group them all together and they compete in order to produce an outcome. And how do you produce an outcome since we don't have the inner product computations that renders the dimension of the input obsolete, it is crossed out, let's say. What we're doing is that the competition is performed on a position-wise basis. So each feature map competes for each position of the output. You can see here in the schematic that we have 2 feature maps in a particular convolutional LWTA block, and each feature map will have different positions, different pixels activated according to the outcome of the competition. Again, it will be a stochastic local winner takes all approach in this specific case. So instead of grouping linear units that perform the standard inner product computation, we group linear feature maps that perform the convolutional operation, and then we decide via the competition function which feature maps contains non-zero values at which positions. So this is done via a principal way, it's not ad hoc, via competitive random sampling procedure, again, that we will describe in the next slide. So basically for each position, only the winner feature map for that specific position has a non-zero entry. All the rest contain a 0 values. This leads us to sparse feature maps with uniquely activated positions. So we can reap the benefits of sparse representations, and as we will see, the robustness and other capabilities that this endows the network with. So in this case, the output of the layer is a little more complicated to explain, but basically what are we doing is its feature map in its convolutional LWTA block computes its, let's say, activation, which is given by the convolutional operation. As we see, HB, U is equal to WB, U convolution with the input tensor X. And then we need to introduce an appropriate winner posterior distribution for each block and for each position. As we said, the competition is a position-wise basis, in order to determine which feature maps have non-zero values at which positions in the specific output. So this is done again with the categorical distribution, where we take the activations, the convolutional activations of each feature map for each position, we pass them through a softmax, let's say, activation function, a softmax transformation, in order to produce probabilities of activation on a position-wise basis. So we can use these indicators. Now they're basically a matrix that we're estimating, and we use this matrix multiplied by the activation of each feature map in each block and get the final output, as we can see, both in equations and in the schematic form given on this slide. So we again resort to evidence lower bound maximization, of course, in order to perform training and inference. And all that we said about the training and prediction in the dense case applies to the convolutional case as also. So we tried this mechanism back in 2019 in our ICML paper, non-parametric, that was combined with some non-parametric Bayesian distributions. And we saw that in the beginning, we had very good pruning and compression capabilities, as well as retaining high classification accuracy. In the recent years, we have been especially interested in the adversarial attacks and adversarial robustness, as we saw in the first slides. And our most recent work, that was part of the Bayesian Deep Learning NIPS workshop, was the stochastic local winner-takes-all networks that enable profound adversarial robustness. As we said, deep architectures are highly susceptible against adversarial examples. So an attacker may induce some small perturbations that can fool a specific model, a state-of-the-art model, into misclassification. So we start from a data point X, and we construct some adversarial examples through various methods. Let's say the fast gradient sign method, the Carlini-Wegner laws, the projected gradient descent, which is the most well-known, and that is constructed, this adversarial example is constructed via an iterative scheme where we're taking small steps in an L ball, let's say an L infinite norm or an L2 ball, and we're taking small steps towards a direction. So if you see the adversarial examples that an adversary has crafted, usually we can't see any difference. They're imperceptible to the average human. So it's not that we're doing something extreme and they are fooling the models into misclassifying something that is greatly transformed or something. There is minor noise added to specific examples in order to fool the models into misclassification. So there are various defense mechanisms against these kind of attacks. The one is stochasticity. There are adversarial training, adversarial defenses. Generative adversarial networks are used in order to understand if the distribution of the original sample is the same as the adversarial attacked, the adversarial examples, and so on. So in this case, we resort to adversarial training combined with our stochastic arguments based on the stochastic local winner takes all activations that we described before. And we saw that we will say, let's say first how we did it and then the results. So what are we doing in adversarial training? We take each example. This is the usual approach in the literature. And for each training point in the dataset, let's say NIST, CIFAR, and all that, we produce the adversarial example and feed it to the model in order to perform training with it. So basically, we augment the training set with adversarial examples in order for the model to know, to learn how to distinguish the clean and the adversarial examples. So in our experiments, we consider some state-of-the-art wide-range networks, employing very low nonlinearities and the stochastic LWTA layers, the stochastic LWTA rationale, as we described before. We examined the splitting of the architecture to blocks comprising two linear units or two feature maps in the convolutional case. In all our experiments and in all our papers and all our work in general, what are we doing is that the number of blocks B that we select and the competitors therein correspond to the number of original units or feature maps in the rule-based baselines. So we're not saying that we have 2 times more parameters, that half of them, for example, are 0 because we have 2 competitors. If we have K linear units in a ReLU-based layer, then in an LWTA layer, we will have B times U equals K. It is a different matter if that half of them or 1/4 of them are turned off due to the competition process. So basically, size-wise, we're always comparable with the original architectures. So we train the models with adversarial training with the exact same way. And we use the CIFAR-10 dataset for this. The first set of experiments concerns attacking the model with a conventional PGD attack. The PGD attack it was an iterative scheme, as we mentioned. We used 20 steps and a specific step size. These are taken from the literature, they're not ad hoc. These are used in the adversarial setting. And we can see the difference between the baseline and the stochastic LWTA. Let's begin with a natural accuracy, because I forgot to mention that when we're doing adversarial training, usually the models suffer from a decrease in the original accuracy of the model. So basically, if we have a wide range net that achieves 90% on CIFAR-10, if we do adversarial training, we might drop down to 80% max accuracy. We can see that in the first columns. We consider the natural accuracy. What is the natural accuracy? It's the accuracy of the clean examples, not the adversarial examples. So we train the model, augment it with some adversarial examples, and we test the model with the original CIFAR-10 dataset. we can see that for different weighted factors, the difference between the baseline, that means the ReLU-based networks, and the stochastic LWTA networks is massive. So basically, we did adversarial training for ReLU. The baseline had a natural accuracy of 74%, and the stochastic LWTA networks had a natural accuracy of 87%. The same applies to the different weighted factors. So we can already see that using adversarial training in order to make models more robust does not lead to a severe performance drop in our case using the stochastic LWTA, but the baseline does. And these baseline results are proved over and over again in different papers. It's not that we did some experiments that we did something wrong with the ReLU-based ones. These are taken from the literature. Now, turning to the robust accuracy, we can see that the results are even more impressive. What are we seeing? That the baseline, the robust accuracy, corresponds to using adversarial examples to attack the model. So the ReLU baseline model for weighted factor 1 had a 74% accuracy in the clean examples. And using the adversarial examples, this accuracy dropped to around 50%, 50 to 55 for all the weighted factors. Instead, we see that stochastic LWTA, of course, sees some minor drops in accuracy, but we get a 30%, at least 30% difference with the baseline. So instead of dropping our accuracy by 20%, as we saw in the ReLU-based case, as we see in the ReLU-based case, we have a drop of around 5.1%. So we can see that the networks are not breaking down when we're doing an adversarial attack, but instead keep a very high classification accuracy. And we can see that this impressive results in comparing our model, the stochastic LWTA models with PCT training with other state-of-the-art methods in the auto attack framework. Auto attack is a framework that is used for some powerful adversarial attacks in order to test the models for the various defenses that one may use. So whatever you see here is considered a state-of-the-art result, a state-of-the-art accuracy. So you have the, let's say, the RST or the Hydra works that are around 60% robust accuracy, or have 82%, and they use additional unlabeled data and some complicated training schemes in order to achieve these results. Instead, all we do is replace the conventional non-linear activations, let's say ReLU, with the principal design paradigm of stochastic LWTA and adversarial training. And we can see that compared to even the next best state-of-the-art that achieves 65.88%, we have 17% better accuracy in the adversarial setting. So we did that. We tested some other approaches as well. How they are saying that when you use stochastic defenses, there are some ways to circumvent that. But we tried that and we didn't see any drop in accuracy. You can see it in our paper. And we posit that the LWTA mechanism is a way forward in a lot of aspects of the deep neural networks. We have the results in adversarial training that, as you see, the numbers speak, they are impressive. We have also some very important results using sign language translation with transformers and stochastic LWTA activations. We also have some recent paper, a AAAI paper with mutual information and stochastic local winner takes all, and the diversification of the emerging representations of the modern networks. And we're trying to solve some very important research questions, because I don't know how many of you have heard of the LWTA rationale and the local competition rationale, and not just the conventional ReLU based on linearities. And we're trying to solve some questions, to answer some questions. So how, for example, is there any latent information that is of discriminative nature in the winner patterns? So what we have observed there is that different classes, let's say in a classification setting, have completely different linear distributions of the latent vectors Xi that we mentioned. So basically, when we go and take the average activations for each specific class, we see that the patterns are different, and thus this can help encode some latent information that helps the discriminative operation of the network. So what we are trying to do at this moment is seek some insight on why the network produces such a specific output. So compared to the ReLU-based paradigm that we have a way via the latent indicators. There are discrete latent indicators, 0 and 1s, and we're trying to see why when we present an image or when we present some text or something, what changes in the patterns and how does that lead to a specific result. And moreover, we had both in the transformer sign language application that I mentioned in the original paper of ICML 2019, we get networks that have a significantly less trainable parameters and compressed in a bitwise manner. So we compress the bits of the weights at prediction time, and we have a much smaller memory and computational footprint. So can we use this LWTA, stochastic LWTA rationale, in order to get networks that have very low energy consumption and serve the goal of green AI? So these are some important research questions among many others that we have, because it's a newly developed algorithm. And we hope that you can find it exciting and experiment with and let us know about what you think. So these are the publications that we have created in the last 3 years. Some of that are at CML, AI Stats, ICCV, and so on. And we're currently working on some other papers. Let's hope for the best for the future. So that was it. Thank you. Sorry if I took too long, but I wasn't prepared time-wise. And are there any questions?
Thanks for your presentation, and time-wise, that was actually perfect. I see we have a question from Andrea. Please go ahead.
Sorry, I don't hear anything.
Can you hear me now?
Yeah, sure.
Sorry, can you hear me now?
Yeah, I can. Can you hear me?
Okay. Thank you for the talk. If we train the model to the same data, I mean 2 times, can it lead to very different overall model due to the stochasticity?
Yeah. For starters, yeah, we have when you're doing a variational base, you have different, and in deep networks in general, different initialization conditions and different maxima, local maxima that you get. So we haven't explored per se the results, but we have seen some different activations and different models. Yeah, so we start from different initial conditions, and due to the elbow maximization, we get down to different final results. But we haven't seen the exact differences because the stochastic nature yields so many different possibilities in order to explore, specific aspects of that. But yeah, we get different results.
Okay, and can it be used beyond classification?
Yes, it can be used. Instead of, we have used it from translation. So basically, the sign language translation task that we did was translating video to text. That's not classification, sequence to sequence. So we have used it there. There are very good results. And we're now looking into more generative models.
Okay, thank you.
No problem, thanks.
Vangeli, please go ahead.
Yeah. So thank you very much, Konstantin. It was for the interesting talk and also for giving this talk. It's at the last moment. actually. So I'm not really, I mean, we're not expert in the field, but just some questions just to understand more. So did you check the variance of the output that you get for a given input? Let's say that you give always the same input. As you said before, you can get different output. If we quantify that with a metric related to PDFs, probability distribution functions, did you estimate the variance or the difference?
We did that in the early works, in 2019, and we saw some difference, but I don't have the metrics in mind, the exact metrics, but that we saw it also visually, the differences.
I'm just curious, how much different is it? Can it be much different, or?
I don't have the exact numbers right now, but yeah, they're usually, I have seen it in the last few months. I did some experiments, so they're changing, but I don't have a metric in mind to mention.
So the values that you report in this table are these the average, let's say, success ratio?
You mean in the tables of the?
Yeah, in this table, for example.
This is the final classification accuracy. It's the same during inference. It doesn't drop depending on the run. When we take 5 samples, let's say, because we said it during inference, during prediction, we take 5 samples in order to reduce that variance that you're talking about. That may lead. It's not much of a difference. If we take 1 sample, it may be 82.5, 82.7, and the average is 82.6. Let's say for multiple samples.
I see. And the follow-up question from the previous one. So, is it possible to apply this for regression problems?
Yeah, it is possible. Whenever you have a network that has some kind of activation, let's say, whatever activation, GLU, Swiss, ReLU, all that, you can replace with this mechanism. So we did some regression. We have some papers, I forgot to mention that, in the financial domain, that we wanted to predict, to make a regression model in order to predict some financial values, some financial metrics, and they work better again than the ReLU variance. So if you just replace in each layer the ReLU nonlinearity with blocks of competing units in the stochastic rationale that we described before, you can use it wherever you like. And nowadays,
the accuracy, does the accuracy depends on the size of the structure of the network?
It's unfortunate that in this day and age, in our papers, we're using the same structure as the original implementation, right? We said that when you have a ReLU-based network, we have the exact same size, but we have half, let's say the output is 0 in its layer. So basically we get half the output 0 and maintain or have even better accuracy than the original counterparts. So of course the structure plays a significant role, but usually and most of the time we're better than the ReLU-based alternative.
Okay, and the last question, just again from curiosity, what about the computational cost?
In the beginning, it's minuscule. It's like 5 or 10% in training, and in inference, it's negligible. You don't have any difference. Because in the training, you need to calculate the KL divergence of the evidence lower bound, and
I'm just wondering, since you have these zeros, whether the computational cost is...
What we haven't done, and we're looking into it now, is exploit some sparse implementations. So sparse inner products, sparse convolutionals, sparse structures in general. If we do that, it will be much faster. So we say that the mechanism is there, and maybe someone that can do sparse structures better than me or the other guys in the group maybe can try that.
Okay, thank you very much.
Thank you.
Nikolaos, would you like to ask your question?
Yeah, thank you for your presentation. It was very nice, very interesting. And I have 2 questions. One is, can you describe a bit your data that you used for training these networks and the distributions that those data follow, or maybe your features?
So you're talking about the specific examples in the adversarial setting, right?
Yeah.
Yeah, so we took Cypher 10. We performed the standard augmentations that are random crop, rotate and all that. The standard routine for, it was written in PyTorch. You know, when you see in tutorial in PyTorch,
Okay.
that's the transformation. And what we did extra is augment the data set with the adversarial examples. So what we did for each example in Cypher 10, we constructed an adversarial example using the PGD approach. This is again standard in the community. We didn't do any extra, you know, feature engineering or something.
Okay.
We just did the adversarial examples.
Okay, so you to train your models, you used let's say standard in the, because I'm not in the field, you used standard, let's say, data sets that you get many people in the field use.
Yeah, benchmark datasets.
Okay.
CIFAR is one of the most well-known.
So do you know, or do you have any idea if you have large correlations in your data, what will be the behavior of your algorithm?
We haven't explored that in particular, but it falls under the rationale that we're looking into that's called specialization. So basically what we're hoping, and we see that the networks are doing, is that the similar examples that in, let's say, classification at least, belong to the same class, tend to get a winner distribution that is similar. So, okay, images, let's say, from similar classes, from, say, the same class with similar attributes, have not the same, but similar probability distributions of activation. Okay. So we haven't exactly examined the correlation between the examples and the final distributions that you mentioned, but we see that similar examples tend to get similar, but not the same distributions in each class. And different classes belong to have different distributions overall. So we're now training on ImageNet, which is a very large data set with 1 million pictures. Maybe there we can get some results, as you mentioned, about the correlation, because there are 1,000 classes.
Okay.
So we'll see how it gets. Yeah.
Very nice. And let's say another question is, so you said that many of your weights actually are with using that stochastic method are going to 0, right?
Not the weights, the units. The weights have their values, let's say all have values, but when you perform the inner product computation between a weight and the input, you produce output, 0 outputs. So we have a sparse representation in the output, not sparse representation in the weights.
In the output of the whole, let's say,
layer. Let's say the layer, yeah.
Okay, could you implement this in the loss function? I mean, the output of the layer, to implement it, for example, with the norm 1, and perform some kind of lasso regression or some other kind of sparse regression. Will this be the same? Do you have any idea on this?
As far as I've seen, if I use some kind of decay for the weights, even simple decay, not L1, L2, let's say, for regularization, there is some minor drop in accuracy. And how I explain that is that because we have this specialization that I talked about before, we need all the weights that we have at our disposal in order to learn the different distributions of the latent vectors. So if we push some weights to 0, essentially we decrease the expressivity of the computations that we perform in this case.
Yeah, but you can regularize directly the output, not the weight. Maybe I'm wrong. I don't know.
Yeah, sorry. So you say that to regularize, when we're talking about regression, to regularize the output of the network to be towards 0.
Yeah.
I guess we can do that. I don't see why not, but I haven't tried it to be honest.
Okay.
So,
I was just curious. Yeah.
Yeah. But whatever you do with, think about this. If it's something, you take away something from this talk, is this, that if you have a ReLU-based network or a deep network that we use in all the papers and the blog posts and everything, you can replace that with local competition in the stochastic.
Yeah. It's a very nice idea. Yeah.
So sure, we hope that many people will see that these results that I presented today, because they're very interesting. But usually, if you don't have something like a ReLU-based architecture, you're not from DeepMind or something, you don't get the exposure that you need in order to push these ideas forward.
Okay, thank you very much.
Thank you.
Andreas, please go ahead.
Yes, implementation-wise, is it easy to convert something that we use and start using this approach?
Yeah, in the first days, 2019 again, when I was writing in TensorFlow, it was the first days of the framework. It was kind of difficult to do this. But now, if you see my GitHub, or in all the papers we have GitHub links, you will see that it is a class, the stochastic LWTA implementation. It's a class of like 10 lines. And when you get to an implementation in PyTorch that says, I call nn.relu, you replace that with the LWTA that we have, and that's it. And you can run everything. Now I was trying a model yesterday. It took me like 5 minutes to change the whole model from ReLU-based implementation to LWTA.
Very, very convenient. Thank you.
Yeah. It took a lot of effort to get to this spot, but if PyTorch implements it inside the library, it will be far easier.
If there are any other questions, people can just unmute their microphones and go ahead and ask. All right, well then, in closing, I wanted to say a big thank you to Konstantinos. Thank you, as Vangelis said, for filling in on such short notice and for giving your presentation, and wishing everyone a good afternoon.
Yeah, thank you for having me, and thank you for your patience, everyone, and hope I'll see you again sometime.
Indeed. All right.
Thank you very much. Bye.
Thank you.
Bye-bye.
Bye.